Hello, I'd like to go over the Pop Quiz 1 and exam and the first half of the material that will be covered on exam 1 using some questions that bring out a lot of the concepts that we've gone over in class. So let's start with a question that was in a test question back in 2015. So let's take a look at how the total energy will change if something is evaporated maintaining 20 degrees Celsius. So what we have to keep in mind is that the total energy is going to be composed of the kinetic energy and the potential energy. The kinetic energy is going to be responsive, the change in kinetic energy is going to be responding to temperature changes, while the change in potential energy is going to be responding to the phase change that occurs. And in evaporation, what we're expecting to see is that we have a lot of particles in the liquid phase, and the liquid has low potential energy, and some of the particles are leaving to go into the gas phase where it's high potential energy. So we expect to see a change in the overall potential energy. And this is not boiling. We want to keep in mind that this is a temperature that is below the boiling point, but there are some fraction of the particles that have enough kinetic energy to escape, right? So it's not all the particles or the majority of the particles having enough kinetic energy. It is just a small fraction. So it's not boiling. So we can assign right away that A and B are incorrect, primarily because there's a region where there's no change in total energy. And we know that this is not allowed because the particles on average are changing at least potential energy. Because they're going from liquid to gas, the average potential energy has to increase, but at constant temperature we know kinetic energy is not changing. So overall, the total energy has to increase because the potential energy is increasing. So both A and B are not allowed in this problem, primarily because there has to be at least an increase in the system because potential energy is increasing. Then we look at two different scenarios, one in which there's a constant change in C and one in which there's a big step in D. In D, that's indicative of a phase change. That's where we would consider boiling or melting, where you have two different phases. You have a big change in potential energy as you go through the phase change, and that's not what's happening here. We are not boiling. So we know D has to be incorrect, and the answer would be C, that we have constant kinetic energy. There's a slow increase of particles into the gas phase as evaporation occurs, and there's a slow, steady increase that's indicative of evaporation. We would pick C. And we're not heating. This is a constant temperature system. We just have slow evaporation, no boiling, a slow increase in total energy. All right, the next question was an activity that we did in class. So let's make sure that if you want to check your notes, you can take a look at the analysis here. So we at the arrowhead, just like we did in class, we call that 0. The potential energy here is ranked as gases in the top, shown there, and liquids to the left. And then we identified in class that each of the distances shown here on the y-axis represent the amount of kinetic energy that we need to supply to separate the particles from liquid into gas, right? And so A is represented there, and it's proportional to the boiling point. So there's the amount of energy, the amount of kinetic energy we have to put in the system to achieve the change in potential energy of the system. B is the same, the amount of kinetic energy needed to be added to separate O2 to O liquid. So the kinetic energy necessary for B is greater than the kinetic energy necessary for A because it's lower on the potential energy curve. That means that the boiling point B for B or for oxygen has to be greater than the boiling point for A. So this is the main argument when you're looking at potential energies of substances that are on the same Peck diagram, that the lower in potential energy they are and they're going up to the gas phase, we can rank the boiling points this way and relate the total amount of kinetic energy necessary to separate them. All right, the next problem was about looking at a pressure versus temperature curve, and what we want to keep in mind is this is just a subset of the general pressure phase diagram, the pressure temperature curve. All we're looking at is the box there, the liquid gas interface. So we're not concerned with the solid, we're not considered with the liquid. And in this particular problem, what we've done is we've superimposed 5 different substances in that box. So we're just looking at the liquid gas interface that would occur in this box, just like the worksheet that we did on Friday. And the general idea here is that liquids are going to be on the top left, low temperatures, high pressures, and gases are always going to be on the bottom of the line to the right, high temperatures, low pressures. Just like we see in the phase diagram. The low potential energy system is there as the liquid. The high potential energy is the gas. And we ranked this in class like this. 0 was the arrowhead. Gases have the highest potential energy, then liquids, and then solids, because the closer the particles are, the lower the potential energy. That was one of our fundamental assumptions in the particulate model. So we're looking at 37 degrees Celsius and atmospheric pressure. That's where the red X is. And now we need to find out, are all these substances liquids, or is one of them a liquid, the rest are gases, or is only one a gas and the rest liquids? And when we do that, we see that all the substances to the right, to the right of that X, they're all in the liquid form, right? They are all above, and that red X is to the top left of those lines, so that's a liquid. While for desflurane, the one dashed line above, the liquid area is above the dashed line, and the gas is below. So desflurane is the only substance in the gas phase under the conditions where the red X is. Everything else is a liquid. That means that the highest potential energy must be desflurane, because isoflurane is a liquid, sevoflurane is a liquid, and they're certainly not the same for all substances. The way you can have the potential energy the same for all substances if they were in the same phase, meaning you have to be above to the left of all substances or below and to the right of all substances. The answer would be A. Okay, so in this question we have a Peck diagram, and there's some specific information here that we want to make sure we feel comfortable applying, that the liquid mixtures are more stable at low temperatures. So that means the mixture, which is M in this diagram, M is more stable at low temperatures or at low kinetic energies. That means when we're looking at the Peck diagram, we see 2 different regions based on the y-axis. The substance that is most stable at low temperature will be on the bottom, and the substance that is less stable at low temperatures will be on the top. So M has to be, the most stable at low temperature has to be on the bottom. So when we take a look at these graphs, we're going to do a dashed line for the bottom. And we see A, yes, the mixture M is below, is the lowest one. It is the most stable at low temperatures. B is not, it is above. It is the less, B is showing that mixture is less stable at higher temperatures. C is showing equal stability and no temperature dependence on stability. And D is showing the same as B, which is that the mixture is less stable at low temperatures or more stable at higher temperatures. So that would choose A. So you want to make sure that based on the temperature data, stability that's given in the problem, you can assign the correct ordering of the potential energy. Keeping in mind that this is only for the Rankine and potential energy. All right, the next question is about, very similar to the first one, where we have a liquid, water, and it is at a constant temperature, and particles are evaporating again. So we would see that the evaporation would lead to an overall increase in potential energy because the gas particles are going to high potential energy in the gas, and the liquid, which is at low potential energy. Temperature is constant, which means that the kinetic energy is held constant while the potential energy is slowly increasing, since we have more particles in the gas phase. So T is constant, kinetic energy is constant. Liquid to gas, potential energy has to increase since the average particle distance is overall increasing, which would lead to this answer, which is that the kinetic energy did not change, but the potential energy increased. Now you want to keep in mind that you should be able to contrast this to heating a liquid up to its boiling point and then heating the gas, which looks something like this, right? Liquid, so with temperature, with time, we're heating a liquid up to through its boiling point and up to the gas. We have two different points, A and B, and so going from A to B, the kinetic energy increases because the temperature increases, and the potential energy increases because we're going from liquid to gas. So in evaporation at constant temperature, the kinetic energy doesn't change, but heating a liquid up to a hot gas, kinetic energy does increase. So you want to make sure you feel comfortable with both of these arguments. It's different than evaporation because of the change in temperatures involved, but overall the potential energy is the same. So we can now finally answer with all of the different ideas we have, that does kinetic energy and potential energy have to increase or decrease together? And now for the clear answer is no, they do not, because in evaporation at constant temperature and heating or cooling of a liquid or solid up to a phase change and beyond, we see that we're going to have two different scenarios. Evaporation at constant temperature, kinetic energy is constant, but the potential energy is increasing. So that's a very different scenario. They're not increasing or decreasing at the same time. So that would be an incorrect total statement that kinetic energy and potential energy have to increase together. While heating a substance from a liquid up to boiling and then into a gas, we see the change in energy versus temperature. We can divide this into three different regions, A, B, and C, which is at A, we're heating a liquid, kinetic energy is increasing, and the potential energy is remaining constant. B is boiling, where kinetic energy is constant, the change in kinetic energy is zero, the potential energy is increasing as we're taking liquid particles and separating them into gas particles. And in C, we see kinetic energy will increase as we heat the gas, and potential energy will remain the same. Right, so these are the scenarios. A, heating a liquid, kinetic energy increases, but potential energy remains constant. B, through the phase change, kinetic energy change is zero while potential energy is increasing. And C, the kinetic energy. So there's really a variety of scenarios with kinetic energy and potential energy. You really have to ask yourself first, to assign kinetic energy change, is temperature changing? If not, the change is zero. If it is increasing, then kinetic energy is increasing, or if temperature is decreasing, kinetic energy is decreasing. Potential energy is about the different phases. Are the phases changing, and if so, in what direction is the average particle distance changing? Going from liquid to gas, the average potential energy will increase. Going from gas to liquid, the average particle will decrease, and potential energy will decrease. All right, so good luck. This is the content for pop quiz number 1, and if you can do these problems and follow along with the then I would suggest you're ready. I suggest taking this content as a quiz and grading yourself based on the answers presented here. This also represents the first half of exam 1. So if you can do these problems, you're ready for the first half of exam 1. All right, good luck everyone.